3 months ago, NVIDIA's CEO announced that his company loses money on every $200 subscription to their premium AI service. Wall Street responded by valuing the company at over $4 trillion, making it the most valuable corporation on Earth. The market has decided that a business model built on selling products below cost represents the future of human productivity. This isn't a story about hype or speculation. This is about a fundamental shift in how value gets created and captured in the global economy. When the most essential technology infrastructure becomes more expensive to operate than it generates in revenue, traditional pricing models break down completely. What emerges instead is something unprecedented: a company that powers nearly everything digital while operating core services at a loss. This discussion is for educational and analytical purposes only and does not constitute financial advice. The contradiction runs deeper than quarterly earnings. NVIDIA controls roughly 90% of the market for artificial intelligence chips, the processors that train and run every major AI system from ChatGPT to autonomous vehicles. Every breakthrough in machine learning, every advancement in robotics, every step toward artificial general intelligence depends on their hardware. Yet the company's most advanced subscription service, the one designed to showcase their capabilities, hemorrhages cash with each new customer. This creates a paradox that traditional business analysis cannot resolve. In normal markets, dominant companies use their position to extract maximum profit. NVIDIA has chosen the opposite path. They have built the infrastructure that every AI company requires, then priced their premium offerings below the cost of delivery. The larger their customer base grows, the more money they lose on operations. Meanwhile, global spending on AI infrastructure continues to accelerate. Technology companies, governments, and research institutions are committing trillions of dollars to build data centers filled with NVIDIA chips. The same hardware that loses money in subscription form generates enormous profits when sold directly. This dual pricing structure suggests something fundamental about how value flows through the AI economy that standard models have not captured. The implications extend beyond one company's financial statements. If the most critical technology of our era cannot be profitably delivered through conventional business models, then the assumptions underlying most economic forecasting may no longer apply. We are watching the emergence of a system where control over essential infrastructure matters more than immediate profitability from that infrastructure. And the reason this hasn't been reflected in price yet is not what most people assume. The visible story begins in 1993, when 3 engineers met regularly at a roadside diner in San Jose to plan a graphics chip company. Jensen Huang, Chris Malachowski, and Curtis Preem had no experience running a business. They incorporated NVIDIA with $200 in cash and a belief that computer graphics would eventually matter for more than video games. Their timing appeared catastrophic. The company's first processor was technically inferior to competitors. By 1996, NVIDIA had burned through most of its capital and laid off half its workforce. Huang negotiated a contract buyout with Sega, admitting their chip was inadequate. The company survived by accepting payment for admittedly defective work. With that survival funding, NVIDIA developed the River 128, their first successful product. Released in 1997, it sold over 1 million units in 4 months. This established NVIDIA as a serious competitor in graphics processing, but their real breakthrough came a decade later with an innovation that seemed unrelated to their core business. In 2007, NVIDIA introduced CUDA, a programming platform that allowed software developers to harness the parallel processing power of graphics chips for non-graphics applications. Before CUDA, programming a graphics processor required extensive knowledge of low-level machine code. CUDA made that same processing power accessible through standard programming languages. The decision to develop CUDA represented a massive investment with no clear return path. Graphics chips were designed for rendering images in video games. Expanding their use to general computation required rebuilding fundamental software architecture. NVIDIA spent years and hundreds of millions of dollars creating tools that would allow researchers in physics, finance, and engineering to use graphics hardware for mathematical calculations. This investment appeared economically irrational. NVIDIA was profitable selling graphics cards to gamers. CUDA required significant ongoing development costs while targeting markets that did not yet exist. Traditional business logic suggested focusing resources on their established customer base rather than speculative new applications. The breakthrough came in 2012 with AlexNet, a neural network that demonstrated unprecedented accuracy in image recognition. The system was trained using 2 NVIDIA graphics cards running CUDA software. For the first time, artificial intelligence researchers had access to computing power that was both affordable and capable of handling the massive parallel calculations required for machine learning. If you're interested in understanding markets beyond headlines, this channel focuses on exactly that. AlexNet's success triggered a cascade of adoption across the artificial intelligence research community. Universities, technology companies, and government laboratories began purchasing NVIDIA hardware not for graphics, but for AI development. The CUDA platform became the standard software environment for machine learning, creating what economists call network effects. As more researchers used NVIDIA's tools, the ecosystem became more valuable to new users. This transformation accelerated through the 2010s as major technology companies launched AI initiatives. Google's TensorFlow, Facebook's PyTorch, and other machine learning frameworks were optimized specifically for NVIDIA hardware. The company invested heavily in software libraries that made their chips run these frameworks more efficiently than any alternative. By 2020, NVIDIA's graphics cards had become essential infrastructure for the technology industry. Training advanced AI models required hundreds or thousands of their processors working in parallel. Major cloud computing providers built entire data centers around NVIDIA hardware. The company's revenue grew from gaming sales to enterprises, from individual consumers to the largest corporations on Earth. The COVID pandemic accelerated this transition, as remote work and digital services increased demand for AI capabilities. NVIDIA's stock price reflected this shift, rising from under $200 per share in early 2020 to over $800 by the end of 2020 and 21. This is the part most people understand. The part that actually changes the outcome comes next. The market narrative treats NVIDIA's dominance as the natural result of superior technology and strategic foresight. Graphics cards happen to be well suited for artificial intelligence. NVIDIA recognized this opportunity early, and their investment in CUDA created sustainable competitive advantages. Success followed innovation, and market value reflected economic reality. This explanation satisfies conventional business analysis, but misses the underlying structural dynamics. NVIDIA's position in the AI economy is not simply the result of better products or smarter strategy. It represents something more fundamental: control over the computational bottleneck that determines the pace of technological progress. Modern AI systems require massive amounts of parallel computation. Training a large language model involves performing trillions of mathematical operations across distributed networks of processors. Running these models for millions of users requires even more computational resources. The mathematics of machine learning creates specific hardware demands that traditional computer processors cannot efficiently meet. NVIDIA's graphics chips excel at this type of computation, but that technical advantage alone does not explain their market position. The critical factor is CUDA, the software platform that makes their hardware accessible to developers. CUDA is not just a programming tool, it is the foundation layer that connects AI software to the physical hardware that runs it. This creates what systems theorists call a dependency lock. Once researchers and companies build their AI systems using CUDA, switching to alternative hardware becomes prohibitively expensive. The software must be rewritten, developers must be retrained, and existing models must be rebuilt from scratch. For organizations that have invested millions or billions in AI development, this switching cost effectively eliminates competition. The lock strengthens with scale. As more companies use NVIDIA hardware, more software gets optimized for their architecture. As more software depends on NVIDIA's tools, alternative chip makers face increasing difficulty attracting customers. Each new AI breakthrough that uses NVIDIA technology makes their platform more essential for the next breakthrough. On the surface, everything still appeared to make sense. The hidden structure becomes visible when examining the economics of AI infrastructure. NVIDIA's chips are not commodities that compete primarily on price. They are specialized tools for performing specific types of computation that determine whether AI projects succeed or fail. This gives NVIDIA pricing power that extends beyond normal market dynamics. A single advanced NVIDIA chip costs between $10,000 and $40,000. Training a state-of-the-art AI model requires thousands of these chips running continuously for weeks or months. The total hardware cost for training one advanced model can exceed $100 million. Yet companies continue purchasing at these prices because no viable alternatives exist for cutting-edge AI development. This pricing structure creates unusual incentive patterns. Technology companies pay enormous upfront costs for NVIDIA hardware, then attempt to recover those investments by selling AI services to end users. The hardware costs are fixed and immediate. The revenue from AI services is variable and delayed. This timing mismatch forces companies to make long-term bets on AI adoption rates. Meanwhile, NVIDIA captures value at the infrastructure level, while AI service providers absorb the risks of market development. If demand for AI services grows slower than expected, NVIDIA has already been paid for the hardware. If new AI models require different types of computation, customers must purchase new hardware rather than upgrading existing systems. The company has also begun offering their own AI services directly to consumers and businesses. These services use the same expensive hardware but are priced to compete with software companies rather than hardware manufacturers. A $200 monthly subscription must cover not only the software development costs, but also the computational resources required to run AI models for each user. This creates an internal contradiction within NVIDIA's business model. Their hardware generates enormous profits when sold to other companies. Their software services operate at a loss when competing against companies that purchase that same hardware. The same computational capacity that creates billions in revenue through chip sales becomes a cost center when delivered as a subscription service. The mathematics of this contradiction are revealing. If NVIDIA's premium AI service loses money at $200 per month, the computational cost of serving each customer exceeds that amount. Given that NVIDIA manufactures the chips and operates the data centers, they have lower infrastructure costs than any competitor. This suggests that premium AI services cannot be profitably delivered at consumer-accessible price points using current technology. Yet global investment in AI infrastructure continues accelerating. Technology companies, governments, and research institutions are committing trillions of dollars to build systems that may not be economically sustainable at current service prices. The assumption driving these investments is that AI capabilities will eventually justify the costs, but the timeline for reaching that point remains unclear. This is where the same forces that drove growth begin to reverse. The computational requirements for advanced AI systems grow exponentially, while the economic models for delivering AI services remain fundamentally unchanged. This creates a widening gap between what these systems cost to operate and what users will pay to access them. As this gap expands, the assumptions underlying trillions of dollars in AI infrastructure investment begin to break down. The pressure manifests first in energy consumption. Training GPT-4 required approximately 25,000 NVIDIA, or 100 chips running continuously for several months, consuming roughly 25 megawatts of electricity. Running inference for millions of daily users requires even more power. A single query to an advanced language model consumes approximately 10 times more electricity than a Google search. Scale this across billions of queries, and the energy costs alone approach the revenue from subscription fees. Data center operators face a similar constraint multiplication. Modern AI models require specialized cooling systems, redundant power supplies, and networking infrastructure capable of moving terabytes of data between processors every second. The physical infrastructure needed to house 10,000 AI chips costs significantly more than the infrastructure for the same number of traditional servers. Real estate, cooling, and power distribution create fixed costs that scale linearly with computational demand. Meanwhile, user expectations continue expanding. Customers expect faster response times, higher quality outputs, and more complex capabilities. Each improvement requires additional computational resources. The latest language models are hundreds of times larger than their predecessors, demanding proportionally more hardware to achieve marginal improvements in performance. This creates a computational arms race, where staying competitive requires exponentially increasing infrastructure investment. The mathematics become more challenging when examining inference costs specifically. Training an AI model is a one-time expense that can be amortized across millions of users. Running that model for each user request is an ongoing operational cost that scales directly with usage. As AI services become more popular, the computational burden grows linearly while subscription prices remain fixed. Success in user acquisition directly translates to increased losses per customer. NVIDIA's subscription service represents the purest expression of this contradiction. They manufacture the chips, operate the data centers, and deliver the software. Their cost structure should be lower than any competitor, yet they still lose money at $200 per month per user. This suggests that the fundamental economics of premium AI services may not support consumer-accessible pricing using current computational architectures. The broader implications extend across the technology industry. Companies building AI products must choose between charging prices that cover computational costs or accepting ongoing losses to build market share. Most have chosen the latter, betting that future improvements in efficiency or increases in user willingness to pay will eventually close the gap. This creates an industry-wide pattern of growth funded by capital rather than revenue. Cloud computing providers face similar pressures. Amazon Web Services, Microsoft Azure, and Google Cloud have invested billions in AI infrastructure to serve enterprise customers. These customers demand access to the latest models and fastest processing speeds. Meeting these requirements forces cloud providers to continuously upgrade hardware, often before previous investments have been fully depreciated. The result is an acceleration in capital expenditure requirements that outpaces revenue growth from AI services. The timing mismatch between investment and returns creates additional stress. Building a modern AI data center requires 12 to 18 months from planning to operation. The AI models that justified the investment may be obsolete before the facility comes online. Rapid technological evolution makes long-term capacity planning extremely difficult, leading to either underinvestment that constrains growth or overinvestment that destroys returns. Research institutions and universities experience these pressures differently, but with similar effects. Academic AI research requires access to cutting-edge hardware to remain competitive. Universities cannot afford to purchase the latest NVIDIA chips at commercial prices, so they rely on cloud computing services or shared research facilities. This creates queues and waiting periods that slow research progress. The most advanced AI research increasingly concentrates at institutions with sufficient capital to maintain private computing infrastructure. Government and military applications add another dimension to the constraint system. National AI initiatives require domestic computational capacity to ensure data security and strategic independence. Countries are investing billions in sovereign AI infrastructure, often duplicating capabilities that already exist in commercial cloud services. This duplication increases global demand for AI hardware while reducing the efficiency of resource allocation. The semiconductor supply chain amplifies these pressures. NVIDIA's most advanced chips require cutting-edge manufacturing processes available from only a few facilities worldwide. Taiwan's Semiconductor Manufacturing Company produces the majority of these processes using specialized equipment that takes years to install and calibrate. Expanding production capacity cannot happen quickly enough to match the exponential growth in demand from AI applications. Memory and storage represent additional bottlenecks. Modern AI models require high bandwidth memory that exceeds the capacity of traditional computing systems. Each NVIDIA H100 chip requires 80 gigabytes of specialized memory that cost thousands of dollars to manufacture. Large AI models need thousands of these memory modules working in parallel. The specialized nature of these components creates supply constraints that persist even when demand is predictable. Power grid limitations constrain data center expansion in many regions. A facility housing 50,000 AI chips requires as much electricity as a small city. Many locations lack the electrical infrastructure to support large-scale AI operations. Building new power generation and transmission capacity takes years and requires regulatory approval that may not be forthcoming. This forces AI companies to distribute their infrastructure across multiple regions, increasing complexity and costs. Cooling systems for AI data centers consume additional electricity and require specialized engineering. The latest AI chips generate more heat per square inch than any previous computer technology. Traditional air cooling systems cannot manage these thermal loads. Liquid cooling and immersion cooling technologies provide solutions but require significant additional investment and ongoing maintenance. The total cost of ownership for AI infrastructure includes substantial ongoing operational expenses beyond the initial hardware purchase. Network bandwidth between data centers becomes critical for distributed AI training. Training large models across multiple facilities requires moving massive datasets and model parameters between locations. The networking infrastructure capable of supporting these data flows costs millions of dollars and requires ongoing capacity expansion. Latency between data centers affects training efficiency. forcing companies to locate facilities closer together and pay premium prices for high-performance networking. The concentration of these constraints in specific geographic regions creates additional risks. Most advanced AI development occurs in areas with existing technology infrastructure, reliable electricity, and skilled technical workforces. This geographic concentration increases vulnerability to local disruptions and drives up real estate and labor costs in these regions. Competition for limited resources in prime locations inflates the total cost of AI infrastructure development. If this kind of structural analysis is useful to you, subscribing helps you stay ahead of the signals markets usually notice last. The system doesn't fail here, it tightens. NVIDIA's position reveals a fundamental mispricing in how markets value infrastructure control versus service delivery. The company has achieved something unprecedented: monopolistic dominance over essential computational infrastructure, while simultaneously demonstrating that premium AI services cannot be profitably delivered at consumer prices. The contradiction persists because the market continues to conflate hardware sales with service economics. NVIDIA's chip business generates extraordinary margins precisely because customers have no alternatives for cutting-edge AI development. Their subscription service loses money because the same computational power that commands premium prices when sold as hardware becomes prohibitively expensive when delivered as ongoing service. This dynamic suggests that the current wave of AI infrastructure investment is built on assumptions about service economics that may not hold. Trillions of dollars are being committed to systems that cannot generate sufficient revenue to cover their operational costs. The infrastructure layer captures value, but the application layer absorbs losses. What would force reassessment is not market sentiment or competitive pressure, but the physical constraints that make premium AI services economically unviable at scale. Energy consumption, cooling requirements, and computational demands create cost floors that subscription pricing cannot breach. These are not temporary inefficiencies that will resolve with scale or innovation. They are structural limitations of current architectures. The market has not yet recognized that NVIDIA's admission of losses on premium services represents a proof of concept for the broader AI economy. If the company with the lowest infrastructure costs cannot deliver these services profitably, the assumptions underlying most AI business models require fundamental revision. This is what remains unpriced, for now,